All right. This is a fun assignment. There's a lot of tricky stuff in here, so I'm more than happy to give some hints. I'm not going to go through and finish any problems, but I can get you at least started and on the right track on some of them. So where should we start? Yes, thanks. 13. 13. Yeah, let's have a look. So they got cosine 4x. I'm definitely starting on that side. So in my mind, there's two ways we could approach 13. Either we're going to think of that cosine 4x as the cosine of 2x plus 2x. Or the other way we could do it is we could think of it as the cosine of 2 times 2x. So we could use an angle addition identity, or we could use a double angle identity. So let's have a look at those two types of identities and see which one's going to get us closer to what we're looking for. So if I look at my angle addition identities, cosine of two things being added together looks like this. And that doesn't inspire me that much compared to what we're trying to get to. My other option, if we use a double angle identity, I kind of like the looks of this one. This looks kind of close to what we're trying to get to, doesn't it? So I think I'm going to go with this. Have you tried that? You went with cosine squared minus sine squared? Okay, yeah. But you see why I'm kind of leaning towards this one? We're trying to get 1 minus something sine and cosine. I kind of like the look of 1 minus 2 sine squared theta. So my hint to you is go with this one. So my first step would be, I'll kind of lead you through the first couple steps. I would start with cosine 4 theta. Hang on, let me get my stuff organized here. I'd start with cosine 4 theta, or 4x. That's equal to cosine of 2 times 2x. And then I'm going with that middle double angle identity, 1 minus 2 sine squared of whatever's being doubled here, which in this case is 2x. And then I'm going to give you one more hint here to get you moving on this. My next step after this would be this. And then I'll let you finish it up from there. It'll all fall into place from there. So that one was tricky because we had choices, and then once we made one choice, then we had another choice. There's a lot of different options, different ways this can go. And I kind of warned you guys at the beginning that with these proofs, it's not always a straight shot. Sometimes you try something, it doesn't work, you go back and you try something else. All right, what else can I get you some hints on? 11. 2 cosecant 2x. We're trying to make this look like cosecant squared x tangent x. So I would start on the left-hand side. And I would start with this move. I don't have any cosecant double angle identities, but we've got a sine double angle identity. Bless you. Do you remember the sine double angle identity? Without looking it up. 2 sine x cosine x. That's going to cancel these 2's. The 2 that's multiplying and the 2 that's dividing here are going to cancel. I'm going to give you one more step here. Actually, 2. I'm going to split it into 2 steps. See if you can find a fancy one that you can squeeze between that 1 over sine and that 1 over cosine. They will get you what you're looking for. What others can we talk about? Number 10. What part of it? You were asked to evaluate tangent 11 pi over 12 twice using sum or difference or double angle identity or half angles. The sum or difference? Yeah. Okay. Let me get my identity going. So we got to find a way to rewrite tangent 11 pi over 12 as tangent of 2 things being added together. You're going to calc next year, right? So we need to stay in radians here. So something pi over 12 plus, what's that? Oh, thank you. Something pi over 12 plus something else pi over 12. So we need to think of different ways to get 11, and then both those angles need to reduce to an angle that's on our unit circle that we're familiar with. So 5 and 6 would be great, except I don't know 5 pi over 12. I know 6 pi over 12. That's the same as pi over 2. So what are some other ways to get 11? Seven and 4. 4 pi over 12 I like. That's pi over 3, but 7 pi over 4 is not going to reduce to anything nice for us. 2 pi over 3 plus pi over 4. 2 pi over 3. What are those in terms of the 11? How about 2 and 9? That works, doesn't it? Because 2 pi over 12 is pi over 6. And 9 pi over 12 is 3 pi over 4. Yeah. Sure. Yeah. That's why I asked if he was going on to calc next year. Because if we're going to be in calc next year, I'd rather have you working in radians. You need to be just as comfortable with radians. You will be just as comfortable with radians as you are with degrees right now. By the time you finish with calc, the more that you can offload this year, the better for you next year. But yes, absolutely, convert it to degrees and look for some angles. So I'm using 30 and what, 125, 135, so 195. Is that what you did? 230 and 135, or did you do 45 and 150? 45, 1, yeah. Either way, it's going to work out for us. Now it's just time to substitute those into the formula. Do you need help with that too? We've done several examples of that. Why don't you give it a shot from here and see how you can do, okay? It's going to work out just like, we've done examples of tangent before, so it's going to work out very similarly to one of those. What else can we talk about? We got time. Yeah. I'm going to give you a hint. I'm not going to do the whole thing. 12 sine 3x equals, we're trying to get sine x and then 3 minus 4 sine squared x. I have no idea. I've done this before, but it's been at least a year. So I'm thinking we rename that sine 3x as x plus 2x, or 2x plus x. I'm going to call it sine x plus 2x. So now I got, is that how you did it? Did you start there? Okay. So we'll go to our angle sum identities for sine. It's sine cosine plus cosine sine x2x, x2x. So this is another one where I'm not too sure what to do with this cosine 2x. We've got three options for that, so I'm gonna work out this part of it because there's only one option for sine 2x. That's 2 sine x cosine x. Let's work out this and see where it gets us. I'm looking at this and my answer doesn't have any cosine x's in it. So I got a feeling that I want this to either factor out or that this is going to end up turning into, we could use a Pythagorean identity on this and turn it into 1 minus sine squared x. I just have an instinct that this is going to turn into 1 minus sine squared x. But that doesn't really tell me what to do with this one up here. I think I'm going to go with the version of cosine 2x that just has sine in it. My instinct is telling me stick with this because what we're trying to get to does not have any cosines in it. The other two versions of cosine 2x have cosines in it. I think I'm going to try this and see what happens there. So this would become sine x and then cosine 2x. The version with only sines is 1 minus 2 sine squared x. Actually, I'm kind of liking that because that term is sort of in the format of this. Yeah, I think we're heading in the right direction here. So what to do next? I think I guess I'll go ahead and multiply that out. I may regret doing that. All right, that gets us to here, and then yeah, we're going to use a Pythagorean identity on this. So this will become sine x minus 2 sine cubed x. There's probably a more efficient way to do this. Cosine squared is 1 minus sine squared x. That's the sine squared plus cosine squared equals 1. But I've sort of rearranged it. And if I multiply that out, we got 2 sine x minus 2 sine cubed x. And that gives us a whole bunch of like terms, and hopefully things will combine to get us the coefficients that we want. So there's one of those, two of them here, so 3 sine x, and then minus 4 sine cubed x. Yeah, I think that'll work. From there, I kind of see factor out a sine, and we got what we're looking for. Again, this is another one where there's like lots of choices with how we deal with it. I'm sure there's another route to get to this. I'm not seeing right now, but the big choice, in a lot of these proofs, the big choices come down to what version of cosine 2x do I want to use. And if you try something and it moves you away from what you're trying to get, it's just not getting any closer to what you're trying to get, then you got to try something else. I've done proofs where like I did half a page of work and then just scrapped it and started over again. And did another half a page of work and that didn't work out either. And then I scrapped it and tried something else. It just, that's real math. That's what happens sometimes with these things. It's not step by step. It's a little bit of guesswork involved. Okay, we still have time. If you guys want to do one more or start you on one more. How'd y'all go with 14 through 17? Were those okay for you? Were those pretty straightforward? Factoring out GCFs and factoring quadratics with trig expressions. There's some difference of squares in there. Yeah. Yeah, 16. Well, there's a good chance there's a mistake on the answer key too. We found a couple of them. So 4 cosine to the third x minus cosine x. So I think I would factor out a cosine x first. 4 cosine squared x minus 1. And that's a difference of squares. So that'd be 2 cosine x plus 1 and 2 cosine x minus 1, and that's as far as I could go. Is that? Oh, you're right. I got to fix that. That's number 16. Thank you. Thank you. Somebody emailed me about one. I don't think it was that one, though. No time like the present. All right. Any others that were weird? Nope. All right. Sorry about that. Yes. Why not? This is all the super fun process we get to do when something goes wrong. Okay, so, all right, now it's fixed. Thank you. All right, let's move on to new stuff. And then if we got some time, we'll come back and go over some more questions if we have them still. Go ahead and grab your packets. We're on our, this morning I said last episode of the unit. Gonna hang on end on a cliffhanger here. This will be our last main episode or main lesson. We're gonna